this lecture, we'll very briefly discuss the idea behind machine learning and its application in engineering. We'll start with some basic definition of machine learning. We'll discuss the use of machine learning in engineering. Machine learning has different terminologies. We'll get familiar with them. And also, there are different types of machine learning. We'll see what are they. In our practice of engineering, we use models, specifically mathematical models, to predict the outcome of certain event. If we give certain input data to our model, it will give us certain output, and that output is the prediction. So before that event actually happens, engineers or scientists want to know what will be the output of that event. And this is absolutely important in all kinds of engineering and scientific practices. In this course also, we have discussed different kinds of models and how we are going to solve them. All these models are mathematical models. So they are expressed in terms of a bunch of equations. They may be algebraic equations or differential or integral equations. We solve them to get the output, which is the prediction of the model. To see some simple example, we can think about the first law of thermodynamics, which all scientists and engineers are familiar with. Here the first law is a model of a system where this del W is the work. This is the output of the system. Del Q is the heat, that is the input to the system. And du is the change in internal energy. In such a system, if we give the input of heat transfer and change in internal energy, we can calculate the work done of a system. Thermodynamics, of course, doesn't give us the actually work done by a system. It gives us the maximum possible work done by a system. But let us not get into all those nitty-gritties here. The main point is that in this model, if we give the heat transfer and internal energy as input, the model will give us an output of the possible work that can be done by the system. This is how this model works. Similarly, if we take some more complicated model, such as this is a model of a wind turbine. The result of the model, what you see here as prediction, this is the output of a calculation. Fluid is flowing and it is creating certain vertical structures, and those structures are seen here in the picture. What this model does is basically it solves these two equations. First equation is del dot U equals 0. Here U is the velocity field and del dot U equals 0 is the mass conservation equation for incompressible flow. The second equation is the momentum conservation equation. The first term is the time derivative of U. The second term is the convection. And then on the other side, I have this del P divided by rho. This del P is the pressure gradient and rho is the density of the fluid. Then I have nu and del square U, that is the Laplacian of velocity vector. Nu is the kinematic viscosity. Both rho and nu are properties of fluid and they are known beforehand. If we solve these two equations, then we can get the velocity field as well as the pressure field P. Once we know velocity and pressure, we can calculate several other quantities of our interest. In this model, the input will be in terms of initial condition, boundary conditions, and the values of these properties such as density, viscosity, as well as the geometry of our solution domain, that is also an input. With those inputs, we go to this model, and this is a difficult model to solve, so we need certain specific algorithm to solve it, which is not part of this course. But if you take a course in computational fluid dynamics, you will learn how to solve such equations. using numerical techniques. Once we solve this equation, we can have our prediction. This prediction here shows the vertical structure which are actually derived from this velocity fields. So you understand the detail of this model or not, that is not important here. What is important here is see that looking at these two models, you see that each model is developed based on certain conservation equation. The first model we have energy conservation. Second model we have mass and momentum conservation. Similarly, we can have model where mass, momentum, energy, all conservation equations are used. So these model equations are developed based on certain mechanism behind it. We know those mechanisms. We have agreed that those mechanisms such as conservation of mass, momentum, energy, they are valid. Based on that, we have developed those equations. Then we are giving input to these equations and we are getting certain solution which are the predictions. So in the second case, before we actually make this wind turbine, actually making a wind turbine is time consuming and also it requires a lot of money. So without doing that, our model gives us a prediction that how this turbine will work, what will be the energy output from it, what will be the stresses on the members, etc. Now, both these models are very nice. When we have such model and we can solve such model, we can get meaningful information from there. However, just like this model, we do not have well accepted mechanistic model all the time. This is called mechanistic in a sense that we know the underlying mechanism of these equations. For instance, here the underlying mechanism in energy conservation. In the second case, the mechanism is mass and momentum conservation. Not always we know them. For many cases, we have no idea about the mechanism. If you are taking this course and you are thinking what will be the outcome of this course, what will be your result in this course, which grade or what kind of marks you will grade in this course, you want to know that, but there is no model that can specifically tell you what kind of marks you can get out of this course. This is a very important problem. This is one of the everyday problems that we think that are important for us, but we do not have a proper model for that. And in fact, most problems for our interest, our everyday interest, they don't have a specific beautiful model like it. And in such cases, what we have is our experience. You certainly did similar type of courses before, or your friends have done similar type of courses before. So if you want to know what will be your result in this course, you may see your previous performance in similar courses, or you may talk to your friends who have taken similar courses. So basically, in absence of a model, we trust on our experience, or in scientific term, we call that we trust on experimental data. In this case, your friends' results are experimental data, as well as your experience in such courses are experimental data. So when we do not have model, only thing we have are experimental data in our hand. In some cases, these data are actually of very high quality, very less error, very less noise there. In some cases, they are not. So their reliability may be questionable, but all we have are certain experimental data. And in such cases, machine learning could be very useful. So what machine learning does? In machine learning terminology, the machine actually doesn't mean an engine or a turbine or a lathe or a milling machine. What it means that the machine is basically a computer program, and it is a program that learns. So unlike the programs that you did in this course previously, for instance, when you are solving an ordinary differential equation, you have a program, you give input, you get certain output. The program doesn't learn anything. Program doesn't change based on this input-output combination. But now, in machine learning, we talk about only those kind of procedure, those kind of program where the program change with this input-output combination or the quality of prediction it makes. So if the program output is something that we are expecting, that is good. But if the program output is something that we are not expecting, or that defies the actual experiment, that defies the real life experience, then the program will change itself so that its prediction can be improved with subsequent inputs. And that is the type of program is something machine learning. So you understand that this part of the course is difficult to proceed if you do not have a knowledge or interest in computer program, because machine learning actually means that machine is a computer program. The definition of machine learning is not something written on stone. It is still an evolving subject, but there is a roughly accepted definition that was given by T.M. Mitchell in this famous book, Machine Learning. This book is available in online for free now, so you can go there and take a look. This book defines machine learning as a computer program. So machine is a computer program that learn from experience E when it is doing some kind of task T, and there is a performance measure of P, and its performance in this task T as measured by P improves with experience E. So the program must be doing something that is measurable. Program gives a output, but how good is that output? That has to be measurable, and that measure is P. And as the program takes more input and gives more output, and we look at the performance measure, or program looks at the performance measure, based on that program will change itself so that this performance measure P improves. So that is the kind of program we are talking about. So keep in mind that machine means a computer program. Without computer program, it is impossible to proceed in the field of machine learning. So when it is useful? Obviously, you have seen this wind turbine problem that we are solving mass and momentum equation and we are getting the result. So when we have such clean model which we can solve and get the result using some of the numerical techniques we have already discussed, when we have this, we really don't need machine learning. So machine learning is primarily useful for such cases. For instance, when we do not have a model, then what do we do? If we have to predict an output of a process, we can take resort of machine learning. Similarly, we have a model, but it is not complete. We have only partial information about the model. Then the machine learning can come and help us to do something about the prediction. Thirdly, we do have a model, but it is too complicated. We cannot solve. At least with our knowledge of numerical methods, we cannot solve. Or even if we can solve, it requires a lot of resources, computational resources that we don't have. In such cases, we can have a reasonable prediction sometimes using machine learning tools. And finally, we do have a model, but the model is ill-posed. Now, ill-posed is something mathematically, it has a very specific meaning, but let us take it in this way that when our model is ill-posed, a small noise in the input data will produce high error in the output. As I mentioned that in engineering, we use model a lot. But one of the fundamental assumptions of all modelings that we discuss in this course as well as we discuss in other course, that if there is a small noise in input, for instance this epsilon, then the output there will be also a small noise, this delta. If for a small input noise the delta is very high, then such model is not a good model. Because in reality, no matter how accurate our algorithm or how accurate our computation is, the input that we give it to a model, this only approximates a real condition. So for example, in that wind turbine model, it is very difficult to give an exact initial condition. In reality, wind speed may vary. So if I calculate the model for certain incoming wind speed, and in reality the wind speed varies a bit, then we will expect that output from the turbine will also vary in a small amount. If for a small change in input, the output changes a lot, then our model will not be very useful in real application. So such models where small noise in input creates large deviation in output, those models are known as ill-posed, and ill-posed models are not really very useful for direct solution, the kind of solution that we have conducted in this course. So in these 4 cases, and we can define many more cases like this, what we do, our lack of appropriate model or our lack of simulation tool or the possibility of ill-posedness of our model, we compensate them using experimental data, which means using our experience. And how we use experimental data to compensate for such lacuna, the tools of machine learning will be very useful there. If we compare with the traditional modeling practices, such as this computational fluid dynamic modeling that I was talking about, if we compare that with the machine learning based modeling practices, there are certain fundamental differences. In machine learning, the models are primarily mechanistic. Mechanistic means that the equations that we are using, there is a fundamental mechanism behind those equations. For example, in most cases, they come from certain conservation equations such as mass conservation, momentum conservation, energy conservation, etc. On the other hand, in machine learning, all these models are empirical, which means they are coming from data. We look at the data and we try to understand that looking from the data, that is our experimental results, our observational results, our experience. Based on that, we try to make up a model without knowing the actual mechanism behind it. And such models, of course, may have certain physical basis. We may think about that certain physical phenomena is happening behind it, and that kind of thinking of ours are known as bias. So here, in traditional modeling practices, what we do is that we are trying to solve a problem, and that problem is basically posed as the input. So in case of wind turbine, for example, we are giving, let us say, wind speed, and we are asking for an output that would be the output power of the turbine. So we give an input and we get the output in our traditional model, and it sounds very obvious. But machine learning models are different. Here what we do, both the problem and solution, which means both the input and output, we give it there in our computer program. And the program learns about the model looking at this input and output. And then once the program learns about this, we give the program one input for which we do not know the output, and we ask the program to provide us an output. That is how machine learning works. So think about a situation when you are solving certain problems from a book, let us say from a chapter of mechanics. You know the theory of mechanics, and using the theory of mechanics, you are solving certain problem. Given every problem, you have a solution, and that solution is developed based on the theory of mechanics. But in case of machine learning, machine doesn't know the theory of mechanics. You give the problem and you also give the solution to the computer program. And then at the end, you give the computer program one problem but do not give the solution. Then the computer program will provide us with the solution. That is how machine learning works. Here in traditional prediction, our models are rigid. Models, they do not change. If our prediction does not match our expectation, in wind turbine case, we cannot go back and change the mass conservation equation. That is not acceptable, because the community, scientific community, have already accepted that mass will be conserved, momentum will be conserved, energy will be conserved. Because I don't like the results, I cannot change those models. We can, of course, change the boundary condition or property. So only less important stuff we can change, but the models we cannot really change. But in machine learning, the models are flexible because we don't know the model or we have no agreement about the model in the community. So models will change with experience. And by experience, especially we means that when the predictions are bad, predictions are not matching with actual experiments, then we can go and change the model, or in other way we can say that the computer program itself will change the model. Finally, because the models are rigid in traditional case, we can only change little bit here and there, such as boundary condition or properties. Here in traditional model, our outputs are deterministic. So we know exactly what will going to happen based on a given input. But here in machine learning, the models are not like that. We are giving certain input, we are getting some output, but we also know that our models are not written on stone. Our models are not agreed upon by the entire community. We don't know the underlying mechanism behind the model. Therefore, all our results that we can get from a machine learning algorithm are actually probabilistic. So we can assign a probability of the output to be correct, or we can give the amount of correctness, we can quantify it in certain way. So they are not deterministic, they are not written on stone. So in machine learning jargon, the output is named as label and the inputs are named as feature. We assume that based on one or more inputs, the computer program or the mathematical model will give us output. The input could be one or more and we call that feature. Output is usually we take it as one output and we call that label. So essentially in machine learning, both the feature and label are data set. Feature is the input data set, label is the output data set. So what we do in machine learning is that the computer program will initially use something we call training data. Training data includes both the feature, that is the input, and the label, that is the output. And through this input-output combination, the computer program will learn about the model. Once the computer program learns adequately about the model, what we do is that we provide test data to the machine, or in a sense that we provide feature but no label. So then the computer program will give us the label which is derived from those features and which uses the model that is already learned from training data. In general, machine learning are of two types. Broadly, there are of course mix of this, but broadly they are of two types. First is supervised learning and second is unsupervised learning. Supervised learning is exactly what we have just discussed. What it does is that it finds the label of test data. How does it find the label of test data? It uses the feature and label of training data to find the label of test data. Unsupervised learning, on the other hand, it uses training data that has no label. It has all features. Looking at the training data, it finds structure in unstructured data, or in other sense that it groups similar data together. And then if I give a test data, it will see that in which group this new data belong. So in this overall discussion, where does artificial neural network come? Artificial neural network is not a different kind of machine learning or anything. Artificial neural network is a technique in machine learning. And this is a technique that is used both in supervised as well as in unsupervised learning. So in our discussion in this course, we have limited time to discuss machine learning. So what we will do that we'll start with general discussion of machine learning and then I'll give you some introduction of artificial neural net. Now to summarize, in this lecture we have discussed the definition of machine learning and we have discussed how it is different with our traditional modeling framework that we have seen in other courses as well as in most part of this course. For your exercise, you identify two practical problems where the traditional modeling method will not be very good and machine learning technique may be used for solution. Thank you. That's all for this lecture, and I'll see you in next class.